Hello, my name is Christine Perret. I'm the chair of the Area Research Committee. It's my pleasure to host this webinar and to welcome you to this exciting topic, sensing human gestures. We're going to be hearing a great deal about the projects of the Future Interface Group. So before I proceed with the webinar, I'd like to thank you all for joining and to remind you that you are in listen-only mode. However, if you would like to ask some questions or make some comments and remarks, you can use the question console in your GoToWebinar control panel. That's how we'd like to take your questions. We do encourage your questions and we'll have time for those after the presentation. So for those of you who may not be aware of the area, we are a nonprofit association, an industry association with 3 groups of members that together represent the enterprise AR ecosystem. I like to say that the top of the pyramid are the enterprises. They are the customers who are going to use or already use augmented reality in their operations to improve performance, reduce risk, and other metrics. Supporting the enterprises in their achievements of better performance and operation are 2 groups: the providers of technologies and services, we call those the provider segment, and they develop a variety of AR enhanced or AR aware products and services for the enterprises. And they also collaborate with non-commercial entities. These are universities, research institutes, and government agencies that are continuously studying new developments and emerging challenges in AR technology. So just a second, I'm going to, Karan, could I ask you to mute your microphone while we're, thank you. So how does the area support the growth of this entire enterprise AR ecosystem? We like to say we have 4 pillars of activity. One is we develop and we help our members to produce thought leadership content. We consolidate, we capture that content and publish it in a variety of different ways, including these webinars and on blog posts and social media, white papers and reports, which are available on our website. We also support networking and discovery sharing between members and the whole AR community about shared problems, shared obstacles, as well as shared solutions that can accelerate the adoption of augmented reality for enterprise use cases. We also collaborate and support programs that educate more professionals that will work in this field and who will, through their performance and their jobs, be able to accelerate the adoption of AR because they have the design skills, the management skills, and so forth to accelerate those projects with fewer roadblocks. Speaking of roadblocks, we have committees that are reducing the barriers to adoption. Our members participate in a variety of committees so that they can share their experiences in a different way, in a more intimate way. And we also produce some deliverables together in those committees, as you may have seen on our website. That's the introduction of the AR for Enterprise Alliance. And now it's my pleasure to welcome Karan Ahuja, who is our guest speaker today. Karan, could I make you presenter, and would you like to introduce yourself and your projects?
Yes, that would be great. Thanks for the introduction. Okay, let me just start.
I see your screen. It just looks great. Thank you. I see your
Okay,
slide.
great.
Perfect.
Great, thanks a lot. All right, good morning, everyone. I'm Karan. I'm a fourth-year PhD student at the Human-Computer Interaction Institute of Carnegie Mellon University. So my research mainly focuses on machine learning and sensing. So what this leads to is applications spanning across various domains, such as health monitoring, activity recognition, context-aware computing, and novel interaction techniques. Today, I will focus on one very important aspect of my work. It's on body digitization in augmented and virtual reality environments. So what do I exactly mean and what would this exactly enable? So full body digitization has the potential to realize a plethora of applications in extended reality systems, such as virtual workspaces. So currently, there's a lot of remote working going on. We're all in our own home. So for example, you can imagine you wear on your headset and you're transported into a virtual office where you can all see and collaborate with one another. So this is an image that I took from spatial.io that tries to achieve this vision with VR headsets. But again, they only currently in their current prototype have hands and upper body working. Another thing that you can imagine something like this would be useful for, full body digitization would be useful for, is something like immersive training applications. So in this case, there's someone who's trying to operate a crane. And you can imagine once you have, instead of joysticks, once you have a more naturalistic control of your whole body, you can have a better sense of embodiment in this virtual representation of yours, and hence have a better control of your environment and around you, and also manipulate things much better. So another extension of this idea is social avatars that people have looked at for a long time, such as companies such as Altspace and Facebook. Reality Labs are really pushing into this domain of what is your accurate representation of yourself into the virtual domain. So along these lines, you have social avatars, but again, right now, mostly while this envision concept, most of these products only capture our hands and our faces to a bit extent. So it's not very personalized right now. In order to enable all these applications and have this embodiment and personalization that I talked about, we really need these sensing mechanisms that can drive this. So we need mechanisms that can sense the full body, hands, and face, as long with the physical appearance of a person, and also contextualizing their immediate environment. To better understand this, what I mean by this, we can look at a high-level design space between instrumentation and fidelity of the digitizer's body. So we can plot these different sensors along this dimension, as you can see here. In general, as we increase the instrumentation of the environment, or the quality of the digitized body also improves. That is, I can get a better pose of myself if I use a higher grade industrial equipment to scan myself, right? Unfortunately, the user burden and cost of this instrumentation also grows in lockstep, as can be seen in this diagonal line, to the point where it becomes infeasible and impractical to deploy them at scale, thus defeating the whole purpose. So let me walk through an example of some of these to explain and really drive my point further. So you have a high fidelity body capture, such as a Vicon, or any other MoCap suit, such as XSense, that can capture your full body and range of motions. That's great. However, it costs north of $10,000, and each user needs to put all these IR LEDs and balls around them to be digitized in this virtual environment. So while great for something like a movie setup where you have an actor sort of in this suit or an actress in this suit and you're capturing their body motions, it's not really practical. You can't really imagine people in a workforce to sort of like go into work every day, strap on their Vicon suits, and then go about their daily lives. So now, on the other hand, you have standalone headsets such as Oculus Quest, which have this idea of a single point instrumentation, and they cost only $100. For example, the Oculus Quest 2, which costs around $350, and it's definitely much more practical and deployable. But again, now you make a trade-off on what you can sense, and in this case, you lose the whole body, and you can sense only the hands of the user. Now, if you extrapolate this further, you can see on the lower end of the spectrum, we have these low fidelity sensors, which are generally much more specific in the types of events they can sense. For example, a pedometer can only return step counts, or a touchscreen can only sense a fingertip's location on the screen. So again, these are customized things that can only tell you a very, very small part of your body, what they're doing. But again, this is like something that's very cheap and commoditized. So I like to call this dashed line that represents these axes of conventional approaches that balance instrumentation cost and sensing fidelity. So much of my prior research also falls along this continuum of the conventional approaches. For instance, in EduSense, which is a project of mine, I used cameras in classrooms to glean insights about students and instructors' body pose, providing university teachers with high quality feedback for professional development. So basically, in this project, we tracked what the students were doing. We digitized their body and could tell whether they're raising their hands, which side of the classroom they're looking at, and all these were detailed analytics that we passed on to the instructor so that they could become better instructors in the future. So in Vid2Doppler, which is another project of mine, we use synthetic Doppler radar training data generated from videos for human activity recognition. So now you had a Doppler sensor which could tell you whether you're clapping, cleaning, cycling, or doing various activities. So that was more along digitization for human activity recognition point of view. So both of these are high fidelity and also require instrumentation of the environment in multiple points. So let's say in EduSense, you required multiple cameras in the classroom, and for this radar project with Vid2Doppler, you required special external sensors in the form of a Doppler radar, and thus they occupy the upper right quadrant of my design space. So ideally, what we want is approaches that do not require as much user or environmental instrumentation, but retain the high fidelity for body digitization to power rich end-user application. So this can be shown in this area in green. So this is where my current research lies and what I'll focus on in my talk today. So to recapitulate, what we ideally want is a system that is self-contained and has low instrumentation cost and can sense your body pose, hand pose and gestures, facial feature tracking, and also enable some form of apparel and skin sensing so as to create a more personalized representation of your body in this virtual avatar or in an augmented reality space. To achieve this vision, the first project that I would like to point out is MeCap, which is on whole body digitization for low-cost AR/VR headsets. So the idea over here was to instrument a single point on the user over your headset and nothing else, and we are trying to get the whole body from it. So we achieved this by using the smartphone's rear-facing camera to view two mirrored half spheres that are placed roughly 15 centimeters in front of the headset. So keep in mind, this was a very, very initial research prototype, and while this looks janky, there's much more appealing version that can be thought of in a commercial prototype. So in a commercial design, we envision being similar to a macro or wide angle camera attachments that are on the headset. So they can provide a view that is very similar to the view that MeCap provides via their fisheye lenses. So at the inception of this project, when we started back in early 2018, Oculus did not roll out with this headset, so we couldn't use it. So that's why we made this sort of prototype with these hemispheres and cantilevered it from a Google Cardboard-based mobile VR headset. And all this sort of like image processing and the computer vision pipeline that I'm going to show you can also run as well on Oculus Rift S, and the similar insights can also be migrated in that domain. So with keeping that in mind, let's go over the technical details of our implementation. So you have this hardware setup in which you have these two sort of spheres placed in front of the mobile VR headset. So this accessory offers a distorted but complete view of the wearer. So basically, when the wearer is wearing it, you can see the reflections of them on the surfaces that you will basically capture to digitize their pose. Although this doesn't seem as much, you can actually unwarp this view from any different viewpoint. And after you unwarp it, you can get a much better equirectangular projection, which basically means that this image is now straightened out and does not have as much curvature as we saw in the previous one. So from this view, we can take advantage of pose-based algorithms to get information about the upper body key joints as well as some lower body till the knees, and also digitize their hands, as you can see over here. Now, given that we have two such views of the user, and we do not have any depth, but we can use the stereo correspondence between these two views and provide them with the missing Z data. As you can see over here, this is digitizing the hand Z that we have digitized using the left and right views from the left sphere and right sphere. Not only that, we can also capture the mouth, at least some parts of the mouth that are visible, and classify it into like neutral, smiling face, or like whether the mouth is open or closed, and provide a very low fidelity digitization. So we can also extract patches from the video and the pose to estimate the person's skin tone and apparel. So in terms of example use applications, you can imagine how this rich data can be used for many end user applications. Currently, when the user has to make a social avatar, The user has to estimate and customize their own skin tone, apparel, along with other attributes in a very manual process. So you can imagine how something like MeCap can be used, and it can be very automatic in nature. So this is something this is where this so MeCap can enable a personalized social avatar. So every time you can put on your device, it can convey not only your body language and gestures, but also apparel. As you can see in this very crude sort of like stick figure avatar that I have over here, but it gets the point across. You can see that the pants are colored blue, the skin tone changes, and so does the shirt color change as soon as the user puts it on. You can imagine a much higher end version of this with graphics in Unity. Um, Similarly, what you can also get is an environmental map around the user. So Apple ARKit Scene currently can estimate ambient light intensity, and based on that, it can shade the augmented reality objects. However, it has no automatic way to compute the environment map for multiple illumination sources. So what I mean by this is when you place a virtual object, you want it to reflect the correct lighting that it has in the space and also the correct reflections of the environment around it. So what you can use is you can use this view from MeCap and use this processed camera data to generate environment maps that you can overlay as diffuse or specular reflection onto these objects, and therefore you can therefore you can model the lighting of the environment back onto these virtual objects, as you can see in the sphere over here. Another use case is gestural interaction, right? For example, you can imagine how you have to choose a tool. For example, in something like Google Brush, it requires you have to point and select something from a very big target list. With MeCap, you can actually use controllerless hand inputs. So for example, you can summon tools by just making the correct gesture for it without the need for any gloves or controllers. Here you can see someone who's like summons a steering wheel for a car or a book or even a soccer ball just by placing their hands in these different orientation, and this sort of like comes back in virtual reality, and the user can use that tool. So while MeCap, what we imagine MeCap to be in the future is like a removable accessory that is of a fisheye cameras. Also for low-cost AR headsets like HoloKit, this accessory would not block the user's view. So you can imagine this being used in HoloLens type prototypes or more AR-based prototypes as well in the future. So that's great. All this it enables, but let's take a quick dive into the accuracy of MeCap, or how good is it, because that would really give us an insight into what kind of applications can we enable with it. Can we even do like very high fidelity capture? So the good thing is we did a 3D spatial accuracy study in which we benchmarked the accuracy of MeCap using a checkerboard pattern in which we already knew the 3D positions, and we back projected them and saw that what is the accuracy of MeCap for 3D spatial accuracy reconstruction. What we found was that there was only a mean equilibrium error of around 2.5 centimeters. To be exact, it was around 2.3 centimeters. And as we moved away from the optical axis, that is, as we moved down below and away from the reflections moved away from the spheres, the error increased, but it wasn't that much. You could still get a very accurate 3D representation of the user's body. So in terms of pose estimation, we did sort of a pose gesture accuracy study in which we sort of asked the users to emulate 8 different poses, as you can see on this figure, with different orientations. And we saw that we could capture the key points 97% of the times we could reconstruct their pose. And we calculated a mean error of 0.3, which is normalized respect to their shoulder width. So if we create the shoulder width as 1 unit of error, MeCap was off by at most 0.3. So for hand gesture recognition, we asked 10 participants to perform 5 one-handed and 5 two-handed gestures. So basically, as you could see in the summoning example, we asked them to do different hand gestures, which is such as a close hand, open hand, an OK sign, or a Spider-Man sign, just to emulate what the different conditions would look like. And we collected this data across 3 sessions, and we found out that our gestural accuracy cross sessions, that is when you train on a data of one user in session 1, you ask them, you calibrate the system in session 1 and test it across different sessions, that accuracy was around 96%. But when you have a model that you train on other users and test it on an unseen user, such that this user you have never used their training data, this is more around 80%. So this is more of the accuracy that you can imagine that would be in the field. Like you do not have to train the system at all. You just wear it and it sort of works out of the box. That was around 80% accurate. Similarly, for mouth state recognition, We asked 10 participants to perform 5 different mouth states, and in this case, the cross-session accuracy was 95%, but across users, there was a severe drop. It was 65%. The reason for this was the way different people perform their mouth gestures, such as mouth open or smiling. It's very different how different people perform the same things, but it's very much similar when you talk about hands, when you have to open your hand or close your hand. It's very much similar, but the expressivity of the mouth and the way they use their muscles, it's something that the literature has recorded is facial expressions change across people and have a higher deviation across different people. So again, coming back to the personalization aspect, it is also very important to test how good we were at apparel tracking and skin color estimation. So for skin color estimation, MeCap was about 90% accurate when benchmarked using a Fitzpatrick scale. So that is, we picked a color and what the user said whether that color actually represented their body skin color or not. Similarly, for shirt and pant color, we showed the participants the MeCap extracted colors, and then the participant rated the quality of it on a Likert scale. And on a scale out of 10, most of the participants liked it on a 7, rated at 7.1 for shirt color and 7 for pant color. So that is the information that we sort of used in an automatic way to capture the personalized avatar that I showed you in the application section of this. So moving on from MeCap, there was a sort of another orthogonal approach that we can take when it comes to user digitization, especially in a multi-user context. So what I mean is an opportunistic user digitization called BodySLAM that I'll go into and explain to you what that exactly means. So BodySLAM takes advantage of an emerging use case, co-located multi-user AR/VR experiences. So I'm going to show you a few clips and let's see whether they have a commonality in them of what I'm going to show you. So although nascent, the application space for paradigms that require multiple users in AR and VR is ranging from a diverse set of multiplayer games, as we can see over here. People are sort of like moving from left to right. Let me just replay this. So you can see that people are pointing their phones from one person to the other, and you can see different people in their field of view. So this is an example of mobile gaming, to where you can see in this example of medicine and healthcare, where different people are wearing these headsets and looking at each other while sort of in this simulated training of surgery. And also to AR augmented collaborative spaces, right? That's the idea that everybody has a HoloLens or a mixed reality headset and you're working on things together. So one commonality that you can see in all these scenarios is that the users look and face each other while they're immersed in these experiences. So this opens up the possibility for an opportunistic capture of other users. Now you can imagine that if one person looks at the other one, person A who's looking at person B can help digitize person B, and person B who's looking at person A can help digitize person A. So that's exactly what we went on and did in BodySLAM. So this is an example of what I said. There are two users A and B that face each other, as you can see over here, perhaps playing a mobile AR game where full body tracking could be very valuable for expressive input. Unfortunately, neither phone is able to see itself and thus digitize the owner's body. However, user B's phone can see user A, and user A phone can see user B through its rear-facing camera. So BodySLAM can make use of this view to capture and digitize the body, hands, and mouth of user A and share this data visualized as A dash back to user A. So user A does the same for user B, providing ad hoc full body tracking without having to instrument either the user or the environment. So each gives their pose to one another, as you can see over here. So this is the core idea behind BodySLAM. Let's walk through an example to see how this works in more than two people. Here you can see users wearing mixed reality headsets playing an augmented reality ball game. So these are the respective views. So these are the respective views of the HMD of each user. As you can notice over here, users can look around and see each other. These are the views from the different people, A, B, C, D, and E. You are seeing what they see from their headsets. To understand what's happening, let's zoom into the view from person C. So this is the view from person C. They see someone in their view. So what will happen first? Well, first they would ID the person that they are viewing. This would mean that they would first get their post points and see where these post points are located, and also detect where the Aruko marker is, and based on that extract an ID of that person. So not only that, they can also relay this information back to them and this person C can tell person A that, hey, this is your pose information, and you can make use of it. Now, taking these different perspectives together, our whole system can digitize one another, and this is what it looks like in action. Like each person digitizes someone and relays their view. So you find the best view for someone and then relay it back to them. Furthermore, in many cases, a user's body can be seen by more than one person. So imagine one person, in this case, person E, is in the view of both person C and D. In such cases, we can also estimate the 3D pose of that person by a stereo reconstruction, as you can see over here. Also, even though I'm currently talking about body pose, in a similar manner, you can capture hand and mouth pose as well. So again, you can use this for something like hand gesture recognition, um, in which you can use the hand poses that we captured and their unit direction vectors to sort of build a gestural recognition tool in which you can classify different gestures such as OK, thumbs up, high five, peace sign, or fist. Again, this is just the library we chose. This can be expanded or like even modified based on whichever gestures the end user wants to capture. Similarly, for mouth state, you can do mouth open, smiling, or neutral. So let's go back to our multi-user scenario and look at some of the other capabilities of BodySLAM. As we just saw, users can't see themselves, and thus everybody is given their pose by someone else. What you can see over here is the top-down view of the scenario. The placements of the video frames here are not arbitrary. They represent the actual positions of these users. So you can see that what person sees, which person sees which one, the other person, and where they are located in this coordinate spectrum if we just take the projection on a 2D screen. So the pairwise information of which user is viewing whom can be used to create a directional graph with spatial information, allowing BodySLAM to compute a global scene in real-world coordinates. So note that users that see no one, such as user E, can still be added to this graph of people if at least one person sees them. So over here, you can see which person is seeing whom, and even though no one is seeing, and even though user E cannot see anyone, they can still be added to the graph. Likewise, a user that is seen by no one, such as person A, can also be added to this graph if they see at least one person. So for example, if A is viewing someone else, but nobody is viewing them, you still know the location of person A relative to the person they are viewing. And you can use that information to also place them in a 3D graph. So now if you take all this together, we now have a global scene topology of the position of the different participants and their pose. So now you have solved not only for the pose of the people, but also their location in this map. And now you have the location, the hands, and also the body pose of these different people. Again, another thing I would like to add is while we created this exemplary prototype in a mixed reality headset, it can also create in other form factors such as a mobile AR or VR modalities as well. So this is what it looked like in our VR form factor. Even though I just showcased you our AR form factor, it can also be extended to these different modalities. Now, similar to MeCap, I will break down the accuracy numbers for BodySLAM. So these are the accuracy numbers for the body, hands, and face digitization over here. The body gestures are around 96% accurate, hand gestures are 88%, and mouth states are about 91% accurate. For a detailed breakdown and information of how I came about these numbers, you can refer to the published paper that you can get from my website that I'll link to at the end of this presentation. But basically, I won't walk you and bore you with all the details. You can sort of go there and look at it to understand the main points. So another key point to remember in BodySLAM, that unlike MeCap, it is very opportunistic in nature. That is, only when you see someone else can you get their body pose. So it is very important to quantify how many times is a person visible or seen in our global scene. In other words, at any given time, what is the percentage of total users captured by our system? So we found out that at random at any given point, about 95% of the users across different group sizes ranging from 2 to 5 people are captured. So if you have a group of about 2 to 5 people, 95% of them would be captured at any time because of these wide angle cameras that we're using that are very popular now on mobile headsets. So also to simulate what this would feel like in other settings when we grow the number of users more than 5 to maybe let's say 100, we ran a simulation study for larger groups in which we placed different people in different sizes rooms with different body orientations. So one body orientation was random, in which they are facing any direction, and the other one was a common focal point to simulate scenarios such as a conference setting or a stadium setting. And we found that the performance improves as the number of the users in a space grows. So as we had more users in the space, you can see that the number of people captured grows exponentially along with it. But not exponentially for something like a 3x3 room, but it grows a lot for something like a 10x10 room. And even if you expand it further, the growth is much more exponential. So while I showcase the use of mobile AR and VR headsets here, for example, in this prototype that I showed you in all these slides, we were looking at something that was akin to a Google Cardboard that was instrumented with it. BodySLAM can run on many other existing headsets with outward-facing cameras, such as the HTC Vive Focus or the Lenovo Mirage. So all these cameras have a high field of view, which is great. It is around a field of view of around 90-95 degrees, which because they want to give the user with inside-out tracking, which is perfect for something like BodySLAM. So now you can also accurately capture where other users are, create a 3D graph of people, and also capture their hands, face, and other modalities such as appearance. So it is important to note, while all these systems such as MeCap and BodySLAM had promising results, there are several limitations that need to be addressed before our system is ready for deployment. So first is there's a heavy compute requirement, as comes with any computer vision system that is sort of runs on consumer end hardware, right? You have to run all these pipelines for pose estimation, unwarping, and other image processing pipelines such as environmental reflection and diffuse map creation, which takes a heavy load on it. So therefore, you need to make use of these neural processing chips and all this hardware, accelerated deep learning expertise that is growing out there, and make use of all those frameworks to sort of accelerate these processing pipelines as well. And the second biggest thing is it needs a better industrial design. So right now, this is very true for MeCap, that currently you have something like cantilevered in front of your face, but you want to use something like wide angle cameras moving ahead. And that is sort of like we're at the V0 of the pipeline for that. And sort of you have to extrapolate for that and sort of get to it a point where it is much more rigid and something that can ship in a much better form factor. And also as a much better field of view, because some of these camera space developments are truly amazing. And you have a 120-degree field of view camera, which can not only just capture your body up to knees, but it also can go lower. And the camera space technology, especially in the field of view domain, is also increasing a lot on the mobile phone sector as well. So you can imagine that the field of view of BodySLAM with a higher field of view, you can capture more people around you and also capture the environment much better. So in these prior slides, while I have talked about work that is already published and that you can find out there, I wanted to quickly give you a sneak peek of some of the research that is very related to what we discussed, but something that we just did and what is debuting at the upcoming CHI conference, that is CHI 2021. So that is on Pose on the Go. So Pose on the Go is a full body yet zero cost motion capture system that makes use of sensors already found in today's smartphones, thus requiring no extra or external hardware. To achieve this, it uses a sensor fusion approach. So in Pose on the Go, what we went out with was, imagine you have a smartphone. Take a top of the line smartphone, such as an iPhone. Using all the sensors of the iPhone, how much of a user's body can you actually capture? So you have a front-facing camera, you have a front-facing depth camera, you have an amazing wide field of view rear camera, you have the IMU and the touchscreen. So given these 5 sensors, let's see what we can do. So using the front-facing camera, we can capture the relative spatial position between the head and hand holding the phone, right? You can estimate the person's head pose, and you can see that by the green vector here. You can also look at what their eyes are seeing in this world. And based on that, you can also see how far their head is from their hands, just from the relative size of the head. Again, for data such as the wrist and elbow locations, we can use inverse kinematics to animate the probable body poses for those ones. Simultaneously, you can use the IMU for the hand capturing the phone and the magnetometer's gravity vector to orient the phone on the user's hand, as well as the head with respect to the world, as you can see over here. Now that the hand that is not holding the phone can generally not be seen or tracked, except when the user touches the screen, which then allows to estimate the finger and the arm position of the hand touching the screen, as you can see over here. Again, using the phone's front-facing depth camera, we can compute a chest normal. So using this depth map, we can actually orient the person's chest and rotate the chest to sort of mirror that of the real world and get their torso orientation independently from that of the head. So now great, we have captured most of the upper body. But one more thing we can do is we can animate the legs despite having no sensor data below the torso. First, what we can do is look at this data over time and use the phone's locomotion mode prediction to load the correct chromatic scheme, such as whether the person is standing, running, or walking. And then you can use IMU and Visual SLAM to coarsely animate the avatar's legs at an appropriate speed. Because now you're not only using dead reckoning from the IMU, you're also using Visual SLAM aspect of it. You can get a very good representation of where the phone is. Finally, using this software, we can combine it and use the head orientation that we got from our previous steps and also this motion predictions, and then combine it all and use high data to solve in an inverse kinematic solver. And you can tell whether the person is standing, sitting down, or also in different objects as we saw just now. So we performed a series of studies to benchmark how good was Pose on the Go against a commercial professional grade optical tracking system. In this case, we just benchmarked it with Vicon. Although Pose on the Go was unsurprisingly less spatially accurate, the estimated pose was more than sufficient to power a wide variety of new and interesting applications. So again, for the details of how much was the accuracy of different parts of it, you can refer to the paper that will be available soon. For example, it could enable new full-body mobile gaming experiences, such as a fantasy game, as you can see over here. The person is moving their wand and sort of like spell casting, or this third-person shooter game in which the phone is a laser that's used to aim and shoot, and the workers can freely walk around and duck behind scenes. It could be also used in health and wellness applications. For instance, phones could automatically count exercise repetitions and track the performance quality. Over here, the person is squatting and it can tell how many squats did the person do. In this app, you can imagine a physical rehabilitation and therapy regimen in which someone is asked to reach different parts of the screen. Similarly, and my favorite is you can extend today's face-centric and emojis to full-body animations, thus allowing for a much more expressive communication, as you can see with this bear example over here. And now you can also like sort of walk off because you actually have the 3D information. So this wraps up my presentation. Thanks so much for attending the talk. For any questions, please feel free to ask me the questions, or you can even reach out on the email ID shown on the slides if you have a question in the future. And almost all my publications that I've talked about and more details of them are available on my website.
Fabulous. Thank you, Karan. This is really, really interesting. And I know that many people who are part of the area and part of the enterprise ecosystem have encountered the need for these technologies. This is really an interesting suite of body and gesture sensing tools that you've developed. As Karan said, please don't hesitate to put your questions into the question console. You anticipated the easy question that I had, which was looking at the BodySLAM and thinking about the computational complexity of this. You mentioned that it can run on some off-the-shelf devices, but of course, scalability is going to be an issue as you increase the number of people. I found that the results of the simulation were very exciting. That it gets better with very large spaces and more numbers of people was interesting. You in your actual study, did you limit the number of people to 5 when you were?
Yes. So in the actual study, given the space constraints and all those things, and also the number of headsets that we needed to for a controlled setting, we limited it to 5 people wearing these headsets. But also another thing, we also created a prototype in which all the processing was happening on device and everything was syncing. So with AR headsets that are basically like smart eyewear, you can imagine that rather than having cameras all around a warehouse tracking people, you can have something like this that people wear with a high field of view, something like 120 degrees. And even though if it's low resolution, with the greatest and greatest in neural processing, you can get the body pose out in a matter of milliseconds, even at 30 frames per second, and interactive frame rates, and you can digitize different people and get their 3D locations as well in those cases. But again, that is something envisioning a form factor that is as a smart eyewear that has a neural processing capability, or at least some processing capability inside of it.
Or it could be connected to edge computing capabilities
Yes,
through a 5G network or a very high-speed local area
yes,
network that,
yes. That is what we
that
did.
would
We
offload.
like,
Yeah,
yeah, we did the offloading route, and we found that that's super useful because then you have the centralized information. So those are the two parallel routes you can go for. One is you can just offload all the compute to a central server or an edge compute device, or you can do it locally and then share the data later on.
sure, sure. Okay. There are two questions that have been entered in the console, and two people would like to ask you questions. So I'm going to first go with the written question. The first one, how can you do dead reckoning with phone IMU? Doesn't the error grow too fast?
Yes, yes, it does. So we are not just using the IMU, we are also using the rear camera view and integrating that, and it's visual SLAM. It's not just dead reckoning. So what I wanted to say was dead reckoning, as you brightly pointed out, has a lot of error. So that's why you have to use the rear camera's features and do visual SLAM to get a much better representation of it.
Okay, thank you. Nigel applauds your research. He says it's fascinating and you made a great presentation, and I agree. Thank you. So how are you investigating, or have you done anything with machine learning and artificial intelligence of the poses post-production? Meaning, you've been studying the real-time calculation and capture of these poses. Can it be even better if you do things offline?
So that is a great question. Let me sort of quickly go to one slide. And yes, I have looked at a lot of it. By trade, I'm like a computer vision and AI researcher before I moved into HCI. So what you can do from this is something that's very close to my heart. So there are two things you can do. One is gestural activity recognition. Given what the hand and body poses are, you can use their unit vectors or also the feature you derive from it to tell what the person is doing. For example, in EduSense, we could tell things like whether a person is raising their hands, what their gesture, or is it cross-armed, or whether they're slouching, and what they're looking at, which part of the screen they're looking at. So that was more of gaze tracking and applications on that, and we made strides into better gaze tracking algorithms. Then the other part is, given you have a pose in which you Doppler, one thing we did was, what is the activity you're doing? So over here from Doppler spectrograms, we made this neat approach in which you could synthesize Doppler training data from actual videos. And so that you did not have to collect any data of your own, which is like a big thing, right? For any deep learning model, you need gigabytes and gigabytes of data. So what we did over here was we created a pipeline in which we could simulate synthetic data. And that was good enough to tell different activities. We could tell whether a person is clapping, cleaning, or even cycling, or even doing exercise counts. It was very good in exercise recognition as well. So for example, whether it's dumbbell lifting or squats, so you can think of various other applications that you can use it to. So I would say human activity recognition is a big one. And the other thing that we have looked at is gestural interaction is a big one. And I would say something that I've not looked at personally, but is a very growing space, is the social aspect of different people interacting with each other.
Sure, sure. Actually, the next question is not far from that topic. It's asking about the hands and arms crossing. You just mentioned that. Is there more you can say or explain about when the hands and arms are crossed?
Yes. So what can you expand a bit? What do you mean by hands and arms crossing? Do you mean that do the hands and arms self-occlude each other, or do they like intersect each other that will result in an erroneous pose, or is it more an occlusion?
So I just unmuted Susan Oslin, so she might be able to ask what she was asking about. Susan, can you unmute yourself locally? Maybe not. Okay. Oh, there
Yeah.
she is. Hi, Susan.
Yeah. So, Hi. I know other systems like the Oculus has a hard time when the hands cross over each other and they can't handle the occlusion. So I'm curious how you're able to.
So in different projects, so for
Thank you.
example, in something like that's a great question because whenever you rely on visual techniques, occlusion is a very important and big factor to deal with, right? If your left arm is in front of your right arm and things like that. So when you go for visual techniques such as MeCap or BodySLAM, that is a big problem for us as well. In MeCap, less so because you have two different views, and that sort of gives you a much better field of view once you resolve it. And even though there is a bit of the overlap, you can change the viewpoint synthetic viewpoint and get a better view in one of those to reconstruct the hands in those cases. But for something that use variables like pose on the go, it's not much of a problem because now you're relying on IMU, which doesn't really care about visual occlusion. And once you use an IK solver behind it, what you actually do is once you have even an erroneous prediction, you can use temporality of human motion dynamics that, hey, one finger cannot intersect the other finger's plane and resolve them using those techniques and sort of get a better representation of which might look accurate. So it's more of like a guess estimate that once you have an initial prediction, you can then streamline it further to solve for no occlusion and use physics-based modules to sort of capture that.
Great. Thank you for that detailed explanation. And you have other fans who are very, very impressed by the work and the analysis, and much appreciated your presenting it here. So we have another question. Someone has raised their hand. Farouk, are you unmuted on your side?
Hi, Farouk
Hi.
Ford Motor Company.
Yes.
Yeah, so I had a question regards to some of your earlier, let's say, models or projects. So when you train your pose estimation model, it's clear you're using vision, and you can infer contrast recognition for the checkerboard example. But what features or variables are you using when training the model for human body? So how are you calculating the nodes that appear to be the moving joints?
Okay, that's a great question. So right now what we did was we unwarped the views in something that current pose estimators can use. And in this case, when this project was done, we all used OpenPose to get the body joints. But from the inception of that and from inception of OpenPose, there are a lot of strides in machine learning algorithms that can estimate a better body pose. And there are different, like computer vision conferences like CVPRs have a full track just dedicated to better pose estimation. So the way they work is, for example, it's like a top-down approach. So first they will figure out the heat maps of the different body joints, and based on that, they would figure out what the locality of these different joints is. So for us in MeCap, the part was to take the image from a very distorted view to a viewpoint to which these different models that are trained on normal videos and scenes, not necessarily taken from this MeCap accessory, can work. So that's why there was a lot of illumination correction that was done. But that was easy because we had the environmental map into the account, which we used to sort of like correct the contrast and then correct the different fisheye like warping in the image. And once we accounted for both of those things, we saw that a lot of the existing paradigms for pose estimation could work directly on those images. But again, that pose estimation is something, rather than training a custom model, we just took the state of the art. But you can imagine that you can fine tune these models or take the latest that is right now in 2020. This was back in 2018. In 2020, there's like even things that can fit a human mesh directly on an image. And you can use those strides in computer vision to get a much better pose estimate here.
Excellent analysis and very clear reply. Thank you, Farouk, and thank you, Karan, for your presentation. At this time, we're finished with the questions from the audience, and I'd like to thank you again, applaud the excellent research, and we look forward to seeing some of these principles and approaches being applied in commercial solutions in the future. Thanks, everybody. This is the end of the Area Research Committee webinar. And if you have any questions or if you'd like to follow up, you can do so with myself or Karan. And this webinar, the archive of this webinar will be sent out to you via email. You'll be able to find it on the Area YouTube channel. Thanks. Bye-bye.
Thanks a lot. Goodbye.